Okay, so we will continue. The last time we have talked about the second classic case of the application of the Faraday's law, which is the case of like an AC generator, where you have a rotating coil exposed in a uniform magnetic field, and when you turn the coil using some energy sources, then this coil will cut the magnetic fields and then it would induce an EMF. And then yesterday last lesson we know that the EMF induced will be varying with time, and the maximum EMF that you will get will be given as E equals to NBA omega, and then the corresponding time period is the 2 power of omega. So well, today we will look in details on this part, and we will officially call it the so-called AC generator. So the name AC generator, it means that it is a device that turns some other forms of energy into electrical energy. So in book 8, when we talk about electives, we will learn more about different types of energy resources that allows us to use so that we can turn them into electrical energy. And well, for example, you can just briefly talk about it here. Is that for example, let's look at the fossil fuel as an example, where you have some fossil fuels and you burn them, and then when this fossil fuel is burned, then it will heat. The heat it releases will be used to boil some water, and it will turn the water into steam, and then the energy will then be converted into the energy carried of the water. Let's say, for example, like this. So it's like that. You have some fossil fuel, and you burn them, and therefore release the heat. So the heat will be released and then absorbed by some water. So this is some water, and then since the water absorb the heat, it will turn into steam, and then this steam will flow, and then it will turn a turbine. So therefore, the steam will turn the turbine. The turbine will be spinning, and then this turbine is then connected to a generator that will generate the electricity. So in a sense, the turbine operates the generator, and the generator produces electricity. So therefore, you need someone to turn the turbine. For the case of the fossil fuels, it is the movement of the steam that turns the turbine, and the movement of the steam comes from the chemical energy released in the fossil fuel. So therefore, generator essentially is just a device which is operated by a turbine, and then it will produce electrical energy. And fossil fuel is just one example. But there may be other examples like the wind power, maybe hydroelectric power. So these are other possibilities. And then they will turning different forms of energy into electrical energy. And the one we will talk about now here is the form of electrical energy in the form of AC. So this is another part, alternating currents. So if you remember, alternating currents will be the types of currents that will vary over time. And we describe this using a peak value. And at the same time, we also introduce the concept of root mean square value of the currents. If you want to talk about if you want to substitute a value to the usual formula of, let's say, P. So for example, you want to use the P, you can use the VRMS. For example, we say P is equals to I squared over R. So for the case of alternating currents, then which current should we use? Then we need to use the root mean square value of the current. And then the root mean square value of the current is given by I naught over square root 2. Okay. Anyway, so this is what we expect to learn in the AC generator. So therefore, the outcome will be an alternating current, and the outcome is to produce electrical energy. So therefore, you will not see a cell or a power supply in an AC generator. Well, another question that some student will ask is, why do we study a generator that produces an AC instead of a DC? Well, with a mind that DC is easier to use. Well, it turns out that there is a big reason why we will attempt to produce alternating current in a generator, because we will want to use a transformer, and because of that, that will be the topic we will discuss next. So anyway, so we look at the AC generator first. So what is an AC generator? So we have to look at a structure of the AC generator. So we have first of all, a uniform magnetic field. So with S and N. I don't draw the magnetic field anymore because I think it will just make the diagram more complicated. You have the coil. You may have a few number of turns of the coil. And this coil, I use the color blue to denote the coil because this coil is movable. It can turn afterwards. And then it is connected to two slip ring. Essentially, it's just a cylinder like this. So therefore, this part of the circuit of the coil is connected to this split ring, and then this part of the coil is connected to the another split ring. So it's like two output, and then they are then connected externally with a fixed carbon brush that allows this turning part to connect to an external circuit. And then this AC current produced maybe then is connected to a resistor and to produce some power. So therefore here we have the slip rings. Sometimes we call it the full ring because it's like a full circle. And then there is a carbon brush. Usually when these two are talked together, then we may call it so-called commutator. And then you have a low outside. And then the corresponding coil will be split or will spin by some external source. So this is like a rotation. There's a turning effect by an external source. For example, the steam will be by the turbine. So this coil is will rotate because it is connected to a turbine. And then when some energy source turn the turbine, then the coil will spin as well. Okay. Now, first of all, you will find out that this setup is very similar to the DC motor. But they are not the same. First of all, the most obvious part is that for a DC motor, it is driven by a dry cell, by DC power source. So therefore, in a DC motor, this part is connected to a cell. So when you compare to a DC motor, so we will not have the load. The load will becomes a power supplies. Well, secondly, when this is a if this is a DC motor, we will not have split rings. We will only have split or just like half ring. Okay, split ring is like two cylinder. It does not have any function like this. And then for each ring is connected to one carbon brush all the time. While on the other hand, for a DC motor, this motor has split ring. That we do not have a full ring anymore, it's just half of it. Like this. And then we have again used the carbon brush to connect it to an external circuit. But this is very important. The difference is, for the case of DC motor, after half of a circle, the split ring will be connected to a different carbon brush. So therefore, it leads to a reverse of current every half of a cycle. So it has this function. But for the split ring, it does not have this function. It's simply just the split ring can only allows the current or EMF induced in the blue coil to the external circuit. But it does not have the function to reverse the polarity itself. So this one, there's no such a function. Okay, now, so we have discussed it last time is that mathematically, we show that the EMF induced in such a case will be a sinusoidal function. And the one reason is because the change in the magnetic flux linkage comes from the variation of theta. And we use the theta to denote it in this way. So therefore, with some derivation last lesson, we found out that the EMF induced is in this form. So this is from last lesson. That we learned the EMF induced here will be given as NBA omega sine omega t. So the maximum EMF induced is given by NBA omega. And we have to pay attention to the fact that omega appears twice. So omega can affect the maximum EMF induced. At the same time, it can also affect the period. Maybe make it a better way. So omega increases, then the maximum EMF increases. While for the maximum, or the omega increases, then it will affect the time period, because the time period is 2 pi over omega, so it will decreases. Okay, it makes sense, because if omega is larger, that means it's spin faster. It's spin faster, that means it takes a smaller amount of time to complete one cycle. So we're looking at the current now, so therefore we just denote the resistance of the load as R. Then the current induced will be just equals to E over R. Then, therefore, we have NBA omega over R and sine omega t. So therefore, this demonstrates to us that the EMF induced is sinusoidal. Therefore, the current produced is also sinusoidal. So the current will be sometimes positive, sometimes negative, sometimes positive, sometimes negative. And then the maximum current is given by NBA omega over R, which is as exact parallel to the EMF induced. Now, there is a question we want to ask. Is that when will so we know that the coil is spinning all the time. Sometimes the coil is vertical, sometimes the coil is horizontal. And in general, it can be any degree. And we want to ask one question is like, when or at which moment is the EMF maximum? And at which moment is the EMF be zero? So this is the corresponding question. Essentially is at what orientation of the coil is the EMF induced zero and maximize. Now there are many ways to answer this question. I want to use the simplest way, which does not need to require any mathematics, is that we need to recall the Faraday's law in the form of cutting of magnetic field lines. One formulation of Faraday's law tells us that if there is a magnetic field line being cut, then we will have EMF. So therefore, when we see that EMF actually can be zero at some instant of time, it means that at some instant of time, there is no cutting of magnetic field lines. So, well, how come? Well, the coil is like rotating, and the coil is always in the magnetic field. It seems that there is no instant of time that the coil is not cutting any magnetic field lines. But if we look closer, it turns out that there is. Well, we look at a sine wheel. And then we have one side is the North Pole, the other side is the South Pole. And then we got magnetic field lines. At this time I put in the magnetic field lines going from north to south. The magnetic field line is constant over time. So even the coil is turning, the magnetic field is constant. Now I want to look at a cross section of the coil, so that now you got a coil here. Let's say a coil like this. So then when the coil is flat, it looks like this. And then the coil will be turned around, let's say for 45 degrees. And then at another instant, the coil is like vertical. Okay, so from here to here is like after a quarter of the period. Now, when the coil is spinning, it's spun by, for example, the motor, not the motor, sorry, by the turbine, then this is what we look like. Now, then you find, actually, I'm not drawing the force, I'm just drawing like its direction of motion. So therefore, you find out that here, sorry. So I'm drawing maybe, for example, drawing the velocity of the coil. So therefore, this is going up like this, going up like this. This is going up like this, going up like this. This is going up like this, going up like this. And you find out that in terms of cutting of magnetic field lines, when this coil is moving up, so it is actually cutting the magnetic field lines. Well, here, when the coil is moving sideways, it's also cutting the magnetic field line, because the magnetic field lines are horizontal. As long as you have any movement in the vertical direction, it will cut the magnetic field lines. However, at the last case here, when the coil is vertical, the side of the coil is moving horizontally. So it has no vertical motion. It means that at this point, there's no cutting of magnetic field lines. So, therefore, we find it. At this instant of time, there is no cutting of magnetic field lines. Because the size of the coil is moving horizontally, or moving parallel to the B field. So as a result, we will conclude that at this instant of time, there is actually no EMF induced at that instant. So therefore, now we understand that in the EMF as a function of time graph, the position of the coil is actually vertical whenever the EMF induced is 0. And whenever the opposite, that means when the coil is horizontal, then that means the EMF induced is maximized. So therefore, when the coil is spinning, and you will go through this 0 EMF, maximum EMF, 0 EMF, maximum EMF, 0 EMF, maximum EMF cycles along the way. Now, then this is a simple AC generator. Okay, now I think that is enough for the AC generator. Now the next thing is we want to look at one part which is not that frequency test, but I also want to talk about it, is using the surge coil to examine magnetic field. So what is a surge coil? Well, surge coil is actually just a coil. It will look like this. So one long rod, and then it will go through many turns, and then go through many turns, and then it come back. What happened? Oh, go through many turns, and then come back like this. This is the surge coil. So this one, you have a certain number of turns. So number of turns is N, and then we of course can talk about the area A. Usually this coil is small, so that you are only covering a small region. And then this output will be then connected to a CRO. If you already forgot what a CRO is, CRO actually is just a voltmeter. You can detect any signal and turn it into a voltage. But this is a good voltmeter because it's different from a usual voltmeter because it can give you a signal as a function of time. So of course there are many ways to do it, many ways to use it, but you can just think about that it will produce a voltage time graph. So if there's nothing happen, there should be no voltage, so therefore it's just always 0. But we have already learned that from Faraday's law, if there is a change in magnetic flux linkage detected by this coil, then there should be an EMF induced. So the Faraday's law here will tell us that if this coil experiences any change in the flux linkage of the coil, then there will be a voltage induced, and that can be detected by the CRO. So therefore, what we hope to do is that we can detect the EMF induced. We can also detect the time for how long it is present. Then we can find the corresponding magnetic field. corresponding to that. Now there are not I think this is not a very, I think for one how to say, it's not a very common apparatus in a secondary school, because somehow not many school not many school have the CLO, and then to teach students to use CLO is also quite time consuming. And also at the same time, I believe that there are already many more user-friendly sensor that are available in the market that can replace it. But anyway, we can of course we do not learn this like a practical skills that we will use this in an experiment, but you can just see this as an application of the Faraday's law. Now let's see. So there are two cases that we'll study to make some concrete discussion. One is that if we have a alternating magnetic field. So case one, that you are detecting an alternating magnetic field. So one possibility, one example would be you have a solenoid. And then this solenoid is connected to an alternating power supply. So therefore, there will be an alternating current flowing through the solenoid. So therefore, sometimes this way, sometimes that way. So I just used a line represented by two heads on both sides. Then there will be induced EMF. There will be a magnetic field that is produced inside the solenoid. So for some instant of time, we'll go this way, where other instant of time will go the other way. So you have an alternating magnetic field. If you have remember, the formula of the magnetic field deep inside the solenoid is actually, we have learned that is B equals to N I L, mu Ni. Where N is the number of turns per unit length, I is the current, and since the current is varying with time, so the magnetic field will also be varying with time. So what we do is that now we have the surge coil, and then we put this surge coil to detect it. We put it inside. Then the surge coil will experience a changing magnetic field. Therefore, there should be a changing. Therefore, there will be EMF induced in the solenoid. So therefore, for the surge coil, it would experience a magnetic flux linkage, which is given as N phi equals to NBA cosine theta. And since you do not turn the solenoid, you do not turn the surge coil, therefore you will have it as NBA because cosine 0 equals to 1. So practically what you do is they try to turn the surge coil until you get the maximum value. So that you are sure that you have to have the cosine theta be the biggest value now. Then after that, then this B is given by mu naught Ni times A. And therefore, everything else is constant except I. So this I is a function of t. When an I is sinusoidal, then your magnetic flux linkage will also be sinusoidal. Then your EMF will be just determined by looking at the gradient of the magnetic flux linkage. Which will be like this. Because you got zero gradient at these 2 points, and you got positive gradient and then negative gradient, so positive value, negative value, and then finally positive gradient, so positive value. So therefore, on the CRO, you will find a shape like this. So you see like a sine curve tracing out in the CRO, as long as you're using the right setting. So therefore, in practice, what we can do is that we can look at how high this value is. Then we can, let's think about it. Yeah, because we know that this is actually, we need to look at the change in time. Let me think carefully how to describe it well. Now, then this is how we detect the EMF. Now, after the detected EMF in the CRO, then we go back to our main question. Our goal is to find the magnetic field strength B. And then you are only given this graph on your CRO. So what we usually do here, then we will look at the Faraday's law. The Faraday's law tells you that EMF is equals to minus change in n phi over change in time. So in one of the interpretation, we say that means delta n phi is equals to minus E delta T. Well, E delta T is interpreted as the area under the ET graph. So therefore, we find an area to study it. In the case of this graph here, let me reproduce it here. We produce this here again. What we can do is that we can look at the graph and then try to find this area. this is the area that we can numerically find because we have this graph. So this, we call it the area. And then on the left hand side of the equations, let me put it like this. So this area then can be found. Now on the left hand side of the equation, we have the delta n phi. Then we look at the corresponding change from here to here, which is in fact from here to here. That means the delta n phi is actually from a n phi maximum value minus the negative of the n phi, the maximum value. So the change is from here to here. So that means you're going from n phi max to minus n phi max. So therefore, in fact, I just have the one on the left hand side to be the negative, to be just 2n phi mass. Well, 2n phi mass will be just 2n magnetic field, the one we want to find, times A. So therefore, the corresponding magnetic field we want to find inside the solenoid will be just equals to the area that we find from the CRO divided by 2 times the number of turns in the search coil times the area of the search coil. So this is how we can find the magnetic field using a search coil. Now, there is another situation, the case 2 we need to study. When the case is not a alternating magnetic field, but it's a constant magnetic field. So hot. Now, constant magnetic field then, at first sight, it would seem constant magnetic field should be easier, but it actually no. Case 2. Constant magnetic field. Well, it's actually not simpler because constant magnetic field means that there will be no change of magnetic flux linkage. Everything constant, there will be no EMF induced. Then how can we induce any EMF to get some data from the CRO? It turns out that it cannot. So therefore, usually what we do for the constant magnetic field, we'll do the following. So let's say you have a constant magnetic field here, and I'm trying to find how strong is this magnetic field. So what we do is actually very low tech. Essentially what you do is that you put the search coil in, and try to rotate it until you got the maximum. You're trying to make sure that it is the normal of the coil is parallel to the B field. And then what you do is that you just suddenly pull it away. Now in doing so, although the magnetic field itself is constant, the magnetic flux linkage of the coil experience is not constant because you move the search coil. So therefore, in the end, there will be EMF induced in the graph, but no longer sinusoidal. With the EMF you induce, it's just like this. Then in this case, the change in the magnetic flux linkage will be just the magnetic flux linkage you have when the coil is in the field minus 0, because there's no magnetic field here, but there's a magnetic field here. So therefore, this time it is actually easier. The area, so E delta T will be the area under the graph, and then E delta T equals to this. Therefore, we have N phi equals to the area, and phi equals to BA. So therefore, B equals to the area over N A. But however, in order for you to do this, you need to repeat it multiple times, because first of all, you see this is not a very, how to say, not a very accurate way to determine the magnetic field. But if you want to use a search coil to find a magnetic field, which is constant in time, then this is the way you can do. It applies the Faraday's law. Without the Faraday's law, without the EM induction, we will not able to have this to happen. Okay. So therefore, today we talk about a stability on the search coil, and a more details on the AC generator. And then for the next lesson, then we need to talk about transformer. And then that will end this chapter. So therefore, like a review, essentially what we're doing here is that we are introducing the Faraday's law. And we look at one important application will be the AC generator. And one reason why we study AC instead of DC is because we want to use transformer. Transformer becomes the most important device. That's why we will frequently say that the electrical energy is the most useful form of energy when we want to for energy transmission. Okay, so we continue next time.